It's a great honor to be the first speaker in this hopefully great series of Nedap Nedap Talks. And today, my name is Max Welling. Here are my affiliations. Work at the University of Amsterdam. I have an affiliation at University of California, and my startup company is Cypher. So we've all heard about big data, I'm sure. Certainly after the Snowden revelations, it's come onto our radar screen more and more. So yes, there's a lot of data at intelligence agencies, but perhaps even more in sort of internet companies like Google and Facebook. In the Netherlands, there's also a lot of data in there are big banks, their financial institutions collect a lot of data about us. And of course, our government has a lot of data as well. But many people talk about big data, but what is really big data? So let's put some numbers on this. So one question one could ask oneself is how much data, how many bits are actually produced, in the entire history of the world? You can try to estimate that. And the current estimate is about 4 zettabyte, and that's a 4 with 21 zeros. Clearly that's not very impressive if you just look at it that way. But if you would put them on today's hard drives, each being about a half terabyte, and every hard drive would be about 5 centimeters thick. And you would pile them up, the pile would be as tall as the distance between the Earth and the Moon. And moreover, this is doubling every 2 years. So in 2 years, it will be twice the distance between the Earth and the Moon. So the biggest data I've been working about, I am going to work with so far, which is a project that I'm involved in, is this astronomy project. It's called the Square Kilometre Array. It's a bunch of antennas spread out over South Africa and Australia, which together make up one big antenna. That produces 1 exabyte of data per day, which is the equivalent of 1,000 petabytes or 1 million terabytes, which is about 1 million hard disks per day. And all of this has become possible because of the growth law, which is known as Moore's law. Moore's law is basically the law that says that every 2 years, the compute power doubles, or the transistors that we're using get smaller and smaller and cheaper and cheaper. And this is plotted in a certain way. It's sort of exponential, a logarithmic scale here and a linear scale there, which basically means that if you see a straight line, it means exponential growth. And we'll see more about exponential growth in a short while. I'm going to claim that there's really 3 exponential growth laws which are relevant for this discussion. So we've already seen the growth of data volume, which is the big data sort of growth law. And I've just mentioned the Moore's law, which is the growth of compute power. But there's a third one, which is the growth law, which underlies the size of our models. And especially this is relevant for a field called deep learning. So it's the capacity of our models, which is also growing exponentially fast, which gives us the power to use all the big data, to exploit the information in big data to make predictions. So what is big data? What is deep learning? So deep learning is basically a revival of a field that artificial intelligence started with, which is neural networks. But we never got these neural networks to really work great. And it's only recently that we got them to work really great. So the idea in this particular version is called a convolutional neural network, is you start with an image, and you have a little template, something that searches for something, maybe an edge, maybe a corner, maybe even an entire face. And this little template or filter is moving over the image and producing output and producing a new image. For instance, this one could be one that's looking for sort of vertical stripes. And we have many of these filters, and these filters are actually learned from the data, and they produce many of these images. So one image is being multiplied into many other images. And then what's happening is we subsample the image. We shrink it to something smaller. And then we repeat. So we are looking for some pattern in this image. We scan over the image and we produce a lot of new images. and we subsample, and we repeat this many layers. And in the end, there's tiny images, and basically this is the information that we feed into an algorithm that tries to predict what's being seen in that particular image. For instance, it could decide that there is a person in the image, a dog in the image, or a chair in the image. Okay, so these type of models have started to work really well. And one of the reasons is that we have been able to grow them really large and train these large models using very, big computer systems. So here's a little history. It's again one of these logarithmic linear plots, which means that a straight line is exponential growth. And in the 40s, at the dawn of artificial intelligence, basically the first neural networks that were being built by hand, they had about 10 neurons in them, very, very tiny, small. And then in the 1990s, there was a famous neural network, which was Nedap, which is a neural network that could sort of talk. That one had 20,000 parameters, or free knobs, things that you could turn. You could set it depending on how, what data you were looking at. And then in 2009, Jeff Hinton gave a talk where he introduced the deep belief net, which was sort of a neural network with as many layers, which was something that we couldn't train before. And he was then talking about around 10 million parameters in that model. And in 2012, I visited Google and Yahoo in Silicon Valley, and they were talking about models that were in the billions, like 10 billion even. I've just put 1 billion here to be a bit conservative. And so if you look at this curve, it's going up on this logarithmic linear, scale, which means that it's actually growing faster at this point, than exponential. But you could take that with a grain of salt. There's only 4 points on this curve, so let's say it's an exponential growth law. And if you extrapolate, you can sort of see that between 2030 and 2050, we might reach in the order of 100 trillion free parameters, which is about the number of synapses we have in our brain. I'm not saying that this machine would be as smart, as humans, because we may not have the algorithms to make them smart, but who knows. So here's a little plot. It's a bit fuzzy because it's basically a print screen from a presentation. So what you see here is the error rate of speech recognition over time. And what we see here is that, there's many years that people tried really hard at companies like Microsoft to reduce that error rate to something so that it would become practical. But they didn't manage. And here, deep learning sort of made its entrance, and this is the error rate, afterwards. And this is the reason that you'll actually have speech recognition on your iPhone and your smartphone right now, because it has surpassed the threshold of being practical. And that's the reason why all these companies are so interested in it right now. Okay, so let's look at data mining for a minute. So what is data mining, or what is machine learning at a somewhat abstract level? You can really think of it as mining in the sense that the data is the ore, and you're trying to find information in that data, which is the gold. And the machine learning tool is the pickaxe. So you're trying to free the information. So let's look at that for a minute. So not all information is useful, though. Here we have an image that's entirely black, and there's actually no information, or very, very little information in that black image. Okay, so here's an image that's basically random noise. And in the traditional engineering sense, there is an enormous amount of information in that image. But none of that information is useful for predicting anything else. Like, let's say you see more images in the future, you won't be able to predict anything with that image. It turns out that the images that we see every day are both loaded with information, but also with useful information with which we can predict the future. So this is where the gold is. For instance, you could train a model on how a tree looks like, and then when you see a new image and a tree appears in that image, you can say, hey, that's a tree. So machine learning works like an information sieve. You have raw information that goes into the machine, and then there is this sieve, And it filters the information in two channels. The first channel is the useful information. And the other channel is the noise. So the useful information is like the gold, and the noise is like the grit, the leftover stones from your ore. And we want to take this useful information and put it into the model, into the parameter. We want to encode it into the parameters of the model so that we can make predictions into the future. And the grit we just want to throw away. So let's do a little experiment here. I won't ask you to take out your tags. But if we look at this, we probably know what this is. No, I'm not going to ask you to write it. So we probably know what this is. But I bet you that nobody has seen this particular object in their lives. I mean, this is something that you have not encountered, I'm pretty sure. Yet you know what this is. Okay, so that's interesting. How did that happen? So the idea is the information sieve again. The information sieve filters out all the information that's unnecessary. It's the Baroque sort of features around it. But it keeps the essence, and the essence can be just indicated with a few lines, like, you know, a seat and some legs, etc. That is the essence, and that's what you want to keep, and that's what's in the parameters of the model. So ironically, knowing can actually be forgetting, but you have to forget the right thing, and you have to remember the essence, which is often, you know, much less than the stuff that you need to throw away. So that's the art of machine learning. And if you have a machine learning system, how would you apply it? Well, you have, let's say, in this particular example, a patient group of which you take sort of scans of their brain, and you have a control group, you know, healthy patients. You train your model, your deep neural network, and in another step, so you now apply your network. A new patient comes in, you don't know whether it's a patient or whether the subject is healthy. You apply it to the network, and the network will tell you this is a patient or this is a healthy subject. Okay, there's one thing which is very important and very dangerous, that is if you put a lot of information in it, you might actually start fitting to that noise, right? This stuff that you should be throwing away, your models might actually try to fit that noise, and that's called overfitting, and that's really the core about machine learning. Avoiding overfitting, but also avoiding underfitting. So here we have a bunch of data points on the x-axis, and we know the y values for these, right? And I want to predict, for instance, here, you know, what will be the value if I would see something on this line here, right? Well, I could draw a linear line here and say that's a pretty good model, so then it would sort of end up here. But we all look at this and say this is a bit of a rough model, right? Because it doesn't really explain this and this data point very well. So let's add some parameters to the model. Now it's a more complex model. It's doing a better job on these, but this one, you know, is not very good. So more parameters, so this model is better, right? Fits through all of them, but not precisely. It doesn't go precisely through all the data points. So here's the best model. Great model, right? Problem is, it's overfitting, right? Because we don't expect, you know, if we measure here, we don't expect that that's going to be the value. We have been fitting to the noise. So we have failed to throw away the right amount of information. And there's a great way to avoid overfitting, to sort of limit the capacity of a model. And this is again something that would be great to do sort of live, but the time does not allow me to do that. And it's called the wisdom of the crowds. And we can actually do the wisdom of the machines as well. And the wisdom of the crowd is, you know, let's all try to estimate the mass or the weight of this cow. Okay, so everybody might just take a guess, right? You know, 800 kilos, 1,000 kilos. You know, you might even say 1,000,000 kilos if you are sort of naive. And then what we do is we order all of these numbers. We just say from smallest to large, and we take the middle number, the number that's right in the middle. And it turns out that that middle number is a really good guess. And we've sort of taken all of your information and put it into one estimate. And that is actually one way to avoid overfitting. Turns out that, you know, the right answer here in this case is about 600 kilograms. Okay, so that's sort of, you know, that's the end of the first part of my talk, which is about machine learning, about the sort of technical part. I also want to talk with you a little bit about the societal impact of of big data and machine learning. So one thing that you can read in the newspapers a lot is is big data actually good for us? Is it not actually dangerous? Right? And there's been a lot of discussion about that. And my response to this is that any technology which becomes more powerful has two sides. Doesn't matter what you're talking about. If it becomes more powerful, there's going to be a good side and there's going to be a bad side. And when humanity invented the axe, in the Stone Age, we were better able to cut down trees and survive. At the same time, we were also better to cut off heads, right, and kill more efficiently. And I would argue that's the ugly side of this invention. And to take things to the extreme, in 1945, 1944, nuclear fission was mastered, right? And the result of this was we could get our hands on really a new large energy source. On the other hand, of course, it also resulted in the nuclear bomb. Now for big data. There is huge potential, and the best example I think for this is personalized medicine. But there's also big dangers, which is like the Big Brother scenario. It's probably not a good idea to live in a country which was like East Germany in the Cold War, when they would have had the sort of big data machinery or the technology that we have today. That would probably have been a quite scary sort of society to live in. So I'm just going to put down some of the advantages and disadvantages, and you can choose what you think is more important. So it could result in a safer society. It could result in a more fair society, right? Today, rich people have access to very good lawyers. Poor people have not access to these really good lawyers. And as if we would have an electronic lawyer, which would be better than both, all humans, that would be quite fair. Then it would level the playing field. Improved healthcare. I will say a little bit more about that, but personalization is going to be, and data-driven healthcare is going to revolutionize healthcare. And comfort, of course, systems that anticipate our every need, like our cell phone, but also self-driving cars, smart homes, you think of it. And then some dangers, clearly privacy violations, right? What would a Google Glass do if everybody would carry it and record everything, and if you make a slip of a tongue, throws it onto YouTube, right? What society would that be? What do internet companies do with our data? What can you use or abuse data for? Identity theft, blackmailing, extortion. Another one I will quickly say something about in a minute is the loss of solidarity in society. If insurance companies will start adjusting their premiums, relative to the probability that something will happen to you, what will be the impact of that? And then unemployment. I actually think unemployment will rise because of AI, but I don't think it's necessarily a bad thing if we divide the wealth more equally. In the US, 3.5 million people are working in the transportation business, and self-driving cars might make a lot of those people unemployed. Okay, I want to say something about anonymized data, because there's a lot of naivete on what it means to anonymize data. And I think it's very important that we learn something about this. I'm not going to go through all of these, but the first one is very interesting. It was an MIT graduate student, LaTanya Sweeney, who was actually able to re-identify the Massachusetts governor, William Weld, using some very simple techniques. And I will say something about this here. So the hospitals were posting basically the anonymized, what they thought were properly anonymized data of, the clinical data of people who would visit that hospital. So here's sort of an example of that. The name, of course, they actually did not publish the name, so they would remove the name. That's what they call anonymization. And then there was zip code and age, and there was gender, and then there was the disease. So this is what was, posted. Okay, and then what she did was she went to the voter registration records, and she found this data, which had the name, the zip code, the age, and the gender. And then she said, well, you know, if I take that number and I take these numbers, they nicely match. And it turns out that if you look at these three numbers, 87% of all Americans can be uniquely identified. And then, of course, we can now match and say Alice had ovarian cancer, right? And there's many, and this is a simple example, but there's many far more sophisticated examples than this. You have to be very careful what it means to anonymize. Predictive insurance. I thought this was a very interesting company. So the company places a accelerometer in your car and measures your driving behavior. If you drive really fast and accelerate very fast, and you know there's also GPS that where you are as well. They say, well, you know, we should probably not lower your insurance premium. But those people who drive really slowly, like me, you know, I would actually get my insurance premium adjusted downward. Great, you would think. But if you do this all the way, then everybody else's premium will have to rise, right? But still, I think it's good to, you know, to encourage people to drive safely. I have nothing against it. But then what would it happen if you take this any further? What about eating habits? You know, if you like hamburgers a lot, are we going to adjust your health insurance premium because you like hamburgers and we know it's not good for you? Maybe, maybe not. You know, smoking might be a clear example. But what if we start to use your DNA? It's not under your control. That sounds really unfair, doesn't it? So we have to be careful. This may be a sliding slope. Here's another interesting example where big data and predictive analytics has caused some stir, which is predictive policing. What if we can actually predict where the crimes will happen? Okay, and in California and in Atlanta, they did this experiment and they reduced crime rates by between 20% and 40%, which is very significant, right? And people, you know, started to contemplate issues like, well, can we actually arrest people before they committed the crime? Right? How scary is it to somebody knocking on your door is, I will arrest you because you will actually commit the crime tomorrow. But so this is somewhat a little bit far-fetched, you know, and there were some movies that sort of were like that. But the one that's more serious, I think, is racial bias. You know, race might actually be a predictor for whether somebody is going to commit a crime. But is that fair? And do we want that in our policies? Well, no, we don't want racial biases in these policies. But they might be interweaved in this data. So we have to be really careful, you know, if we apply these methods. Okay, I want to say a few words about personalized health. So this is one of those exponential laws again. Here, it's the cost of transistors, basically, or the cost of computation going down. Now, this is the cost of sequencing DNA going down, and it followed Moore's law until here, and then it dropped really fast. So fairly soon, you will have your DNA on a credit card, and you will go to the doctor, and the doctor will ask you, can I please read your DNA for a minute, because I want to figure out how much drug I should give you, how sensitive you are to this drug. Okay, so how can this help us? And I think there's really a lot of promise here. 50% of all our medical procedures have currently no data to back up whether they are effective or not. Right? That's a very sorry state of affairs. And many people die every year because the prescribed dose of drugs that they're given is actually not good for them and it's too high. So I envision a system that goes as follows. Patients go to the doctor, they bring their medical records, their genome, and their symptoms because they feel ill. The machine learning algorithm will predict, for instance, whether the probabilities of you having certain disease, and it will produce for you a treatment plan. And the system will follow you to see if it's effective or not, and that data goes back into this big system who can then improve. And you can imagine that if some doctor somewhere in India came up with some procedure and it worked really well, and you look like the same patient, it might be a really good suggestion for you to try the same thing. So, and I can see there can be a huge amount of win here in terms of medical, so the medical world. So the last topic I want to go into is the question whether AI is dangerous. And there has been some recent stir in this. Bill Gates and Stephen Hawking and Elon Musk, not the least of all people, have basically claimed that AI, we have to be really careful about AI because it may take over humanity, right? It might become so smart that it will become dangerous for humanity. So in our sort of sequence of sort of technologies that become good or evil, will AI become our friendly household robot, or will it become some kind of evil Terminator robot? Okay, so we are seriously discussing these questions, and here's my view on this. Current AI is very far from a Terminator scenario. I think it's fair to say we are 100 years out before something that we cannot pull a plug on and will take over the world. By the time this will actually become relevant, the world has changed dramatically, completely, and everything we say today will look laughable in hindsight. So to me, it's a waste of energy to discuss this. Instead, we should focus our energy in solving today's problems, which are really big. Famine, nuclear threat, deadly viruses, health. If we can bring big data and predictive analytics to improve the sorry state of these problems, then I would already be very happy. The end.